All right, welcome to AP Podcast 16.2. This is on entropy and the second law. Now, I briefly touched about this fact that solutions will form because there's many more possible arrangements for dissolved pieces than if they stay separate. You can imagine putting in a little bit of salt, and if entropy is this driving force for disorder, then that salt is going to go ahead and dissolve because there's a lot of more places for those ions to be spread out than if they were just merely clumped together. And we know that entropy is this driving force. So that brings us to the second law of thermodynamics, and that is, in any spontaneous process, there's always an increase in entropy of the universe. I briefly talked about that. Basically, that's just the nature of things. Things move towards disorder rather than order. I talked about a plane falling apart, not building up, something like that. So you think of your room, for example. Again, your room doesn't go towards order, and usually goes towards disorder. So we've got to look at a couple things because it's important that you see these little subscripts here: universe, system, and surrounding, because a lot of times we've got to pay attention to exactly what we're talking about. Usually for us, we're talking about this one right here, the system, whatever we're studying. But we also have to keep in mind what's going on with the surroundings, and the overall process is, of course, what's happening in the universe. So the universe, if the change in entropy is positive, then this process is spontaneous. So therefore, rusting must be have a delta S that's positive. That's why it occurs on its own. At a certain temperature, water will freeze or water will melt on its own. That is a positive process. If the process is negative for the universe, then the opposite process would be positive. That probably makes sense. And if you have a system where, if you have a situation where the universe is at the change in S is 0, then the system is at equilibrium. We haven't really gone over what that is yet, but just imagine that you have the same amount of things happening on both a product side and a reactant side. Nothing's really occurring. Okay. All right, so let's look at a couple things. Now we're going to talk about the surroundings. So if we're looking at the surroundings, it's important that we get this down. If you've got an exothermic process, the surroundings is going to get positive. All right. So imagine you've got this beaker, and you run a reaction, and it generates a bunch of heat. Now think about all the molecules that are surrounding that beaker, which is the surroundings, right? Now that energy is going to go into those molecules, causing them to move around faster, go in more random spots, maybe leave the vicinity, whatever. So what you're talking about is a surrounding having more disorder. On the opposite side of that, if you're talking about the surroundings and we're looking at a endothermic, okay, how in the world can a reaction be endothermic? Well, if this is my beaker, that means from the surrounding area here, energy's got to go in, right? Energy's got to go in. So what is that going to do for the area around here? Well, if we think of heat, it's going to cool off. Maybe we could think of those molecules as moving a little slower in a more ordered fashion, and therefore the entropy for the surroundings is negative. Really important you keep these two things in mind, because oftentimes you will be asked questions on, well, what's going on? Is this process spontaneous or not? And you've got to think of both the surroundings and the system. Okay, so let's look at this reaction right here. We've got water in the liquid state, and it's going to a gas. All right, now you've got to think about this because you've seen this in real life. Water in a liquid state moving to water in the gaseous state. So look and see if these things make sense. Now, the change in entropy for the system is positive. Does that make sense? In other words, is our system going from more order to more disorder? Yes, it is, because I think you guys would all agree that a liquid is more ordered than a gas. So since S is getting more disordered, that's positive, right? Now what about the surroundings? Okay, well, how in the world, from this little reaction, can we figure out what would be going on with the surroundings? Well, think about this. What's the only way we could get liquid to go to a gas? Okay? The only way we could get that to happen is to get energy to flow into the liquid. So, what kind of process are we talking about? Well, we're talking about an endothermic process, and as it says right here, endothermic processes are negative. So, the surroundings is negative. Hopefully that makes sense. Now, what about the change in the universe? Well, that really is going to depend upon the temperature. So there you have it. Just from a perspective of both the universe, the system, and the surroundings. Since we talked about the S in the universe depending on the temperature, let's talk about temperature and spontaneity. All right? Excuse me. So the entropy changes in the surroundings are completely dependent upon the heat flow, whether it's going in or whether it's going out. And if we think about an exothermic giving up heat to the surroundings, that hopefully will make sense that it's going to be more disordered. Now, if we want to really figure out how much, what's the magnitude of the S, we have a little formula that we have to use that involves the entropy and temperature, and that's this formula right here. I like to call this the shoot formula. Though I'll be honest with you, some of my students have given it a different name, but I like to call it the shoot formula. And what this is if you want to calculate the change in entropy for the surroundings, you've got to know the change in enthalpy and the temperature involved. It's a really straightforward equation, but it helps us figure out exactly what kind of change is going on. So let's try one. All right, so we've got this antimony, and it's recovered in two different reactions. And so there they are. You can see that the one reaction gives off a value of a negative 125 kilojoules, and the other one absorbs 778 kilojoules. So calculate the surrounding, the entropy of the surrounding for each of the reactions. Well, let's just do that. Let's use our shoot formula. Delta S equals negative delta H over T. Right? So I'm going to plug in my numbers here, and I've got a delta H of a negative 125 kilojoules over, oh, by the way, I got to make sure that I put that negative sign there. And then the temperature, now we're going to do these in Kelvin, all right? So 25 plus 273 is 298 Kelvin, and that gives us a temperature of 0.419 kilojoules per Kelvin. Now, if you were to look in the back of Appendix 4 in our book, you would notice that the values for delta S are almost always in joules. So you would see a number like this. And that's something we're really going to have to pay attention to later. So that's the process for that one. And let's do the other one. Delta S equals a negative, and then it's 778 kilojoules per 298, which equals, in this case, 2.61 kilojoules per K, which of course is 2,610 joules. Joules per K. Okay. Now let's look at the sign here. Oh, you know what? I left off a sign, didn't I? Okay. Now let's look at the sign and see if this really makes sense, because it's important that it does. So we've got a reaction right here that hopefully you would realize, wow, this is exothermic, right? And this one is endothermic. Now, we're talking about the surroundings. And what did we say before? if you have an exothermic reaction, what happens to the value of the surroundings? It gets more disordered, so S is positive, which, in fact, it is right here, right? And if you have an endothermic reaction, the surroundings are going to get more ordered, which is a negative value. So we've just kind of supported those 2 points about the enthalpy for the surroundings. All right, now that's it for today. If you got any questions, ask me again in class, and I'll see you next time.